Every second, the sun converts 4 million tons of itself into pure energy. That is not a metaphor. 4 million tons of hydrogen become helium, and the leftover mass, the part that does not fit into the helium, becomes light. It becomes heat. It becomes the thing that keeps you alive. And it has been doing this for 4.5 billion years without stopping. Not once, not for a single second. So here is the question. What would happen if it did? What if the sun, just for 1 second, simply was not there? No explosion, no warning, no gradual dimming, just gone. And then, 1 second later, back again, as if nothing happened. The answer is one of the strangest things in all of physics, because on one hand, almost nothing happens. Earth would drift about 3 millimeters off course. The temperature would drop by 24 millionths of a degree. You would not feel it. You would not see it. No instrument on Earth would detect the gravitational change. 3 millimeters on an orbit of 940 million kilometers. That is the ratio of a single grain of sand to the length of California. But on the other hand, the reason we know this, the reason we can say 3 millimeters with confidence instead of just guessing, required 328 years of argument. A machine that can measure 1,000th of the width of a proton and 2 neutron stars that happen to collide 130 million light years away at exactly the right moment for us to be watching. The answer to what happens if the sun disappears for 1 second turns out to be a complete history of humanity's attempt to answer a much deeper question. A question that Isaac Newton called absurd. A question that Pierre-Simon Laplace got brilliantly wrong. A question that took Albert Einstein 8 years of his life and nearly broke him. A question that physicists argued about for an entire century before anyone could test it. That question is this: how does gravity cross empty space? Think about that for a second. You are sitting on a planet that is held in orbit by an object 93 million miles away. There is nothing between you and the sun but vacuum. No rope, no wire, no medium, nothing. And yet the sun is pulling on you right now, this instant, with a force that bends the path of an entire planet. How? How does it do that across empty space? What is the mechanism? And if the sun vanished, how quickly would you know? Newton could not answer this. He knew it, and it tormented him. Laplace tried to answer it, and got a number so wrong, it is almost funny. Einstein answered it, but then spent 20 years doubting his own answer, and the experiment that finally settled it happened on September 14th, 2015, at 5:50 in the morning, when most of the scientists involved were asleep. The universe had been waiting 100 years for someone to build a detector sensitive enough to listen. When they finally did, the signal arrived 3 days before the machine was even officially turned on. That story, the story of how we learned what gravity actually does when the source changes, is the story this video is really about. The 3 millimeters are just where it starts. Let us begin with the 3 millimeters because the physics of that number is beautiful in its precision, and it sets up everything that follows. Earth orbits the sun at 29.78 kilometers per second. That is 107,000 kilometers per hour. If you could drive your car at highway speed toward the sun, it would take you about 170 years to get there. Earth covers that distance in a single year because It is moving at roughly 87 times the speed of sound. You do not feel this motion for the same reason you do not feel the motion of an airplane in smooth flight. There is no wind resistance in space, no turbulence, nothing pushing back. You are in freefall around the sun, and freefall feels like nothing at all. The sun's gravitational pull at Earth's distance is 5.93 millimeters per second squared. That is absurdly weak compared to the gravity you experience standing on the ground, which is 9.8 meters per second squared. The sun's pull is roughly 1/1600th of surface gravity. If you put a ball on a perfectly flat, frictionless table and let only the sun's gravity act on it, the ball would take over 18 minutes to roll 1 centimeter. That is the force holding the entire solar system together. It works not because it is strong, but because it is relentless. It never stops. It has been pulling for 4.5 billion years, and that patient, persistent tug bends Earth's straight-line motion into a circle. Now, if the sun vanishes, that tug vanishes. Earth would continue moving in a straight line, tangent to its orbit, at 29.78 kilometers per second. In 1 second, it would travel 29,784 meters in a straight line. But if the sun was still there, Earth would travel almost exactly the same distance along its curved orbital path. The difference between the straight line and the curve, the tiny gap between where Earth ends up with the sun and where it ends up without, is given by a beautifully simple equation. 1/2 times the acceleration times the time squared. 1/2 times 5.93 millimeters per second squared times 1 second squared, 2.97 millimeters. Call it 3 millimeters. That is the answer to the thought experiment, if all you care about is the orbital mechanics. But here is the thing most people miss entirely when they think about this scenario. The 3 millimeter deviation does not happen the instant the sun vanishes. It cannot. And the reason it cannot is the thing that makes this whole story interesting. When Newton published his law of universal gravitation in 1687, he presented gravity as instantaneous. Mass over here pulls on mass over there right now with no delay. The equation has no time component for propagation. The force simply exists everywhere, all at once, the moment the masses exist. In Newton's framework, if the sun vanished, Earth would know immediately. The gravitational rug would be pulled out from under us at the speed of infinity. Newton was a lot of things. Difficult, vindictive, possibly the most brilliant person who ever lived. But he was not stupid, and he knew that instantaneous action across empty space was deeply, fundamentally suspicious. In a letter to the theologian Richard Bentley, written on February the 25th, 1693, he laid out his discomfort with breathtaking clarity. He wrote that the idea of one body acting on another at a distance through a vacuum, without any mediating substance to carry the force, was, and I am quoting him here, so great an absurdity that no man who has in philosophic matters a competent faculty of thinking could ever fall into it. Think about that. The man who invented the theory of gravity called his own theory absurd. Not the predictions. The predictions were spectacular. The equation worked. It predicted the orbits of the planets. It predicted the tides. It predicted the shape of the Earth. The math was magnificent, but the mechanism was, in Newton's own words, inconceivable. His solution was radical and, in its own way, brilliant. He refused to explain it. In the second edition of the Principia, published in 1713, he added a famous declaration in Latin: hypotheses non fingo. I frame no hypotheses. He was drawing a line in the sand that would influence science for centuries. I can describe what gravity does with extraordinary precision, Newton was saying. I can tell you how it behaves, but I will not speculate about why it behaves that way. That distinction between describing a phenomenon and explaining its cause is essentially the birth of modern empirical science. Newton did not solve the mystery of how gravity crosses empty space. He declared the mystery out of bounds and got on with the mathematics. But the mystery did not go away just because Newton refused to look at it. And the specific question of gravity's speed, whether changes in gravity propagate instantaneously or take time to travel, would haunt physics for more than 2 centuries. Here is why the speed matters. If gravity is instantaneous, then the sun's disappearance would be felt everywhere in the solar system at the same moment. Mercury, Earth, Neptune, all of them would simultaneously lose the sun's pull and begin drifting. But if gravity has a finite speed, then the information about the sun's disappearance would spread outward like a wave. Mercury, closest to the sun at about 46 million miles, would feel it first. Earth, 93 million miles out, would feel it later. Neptune, nearly 3 billion miles away, would not know for hours. And this difference is not academic. If gravity propagated at the speed of light, which is what Einstein would eventually predict, then Earth would continue orbiting normally for 8 minutes and 19 seconds after the sun had already vanished. The sun would be gone, but from Earth's perspective, nothing would have changed. We would still see it shining. We would still feel its pull. For 8 minutes and 19 seconds, we would be orbiting a ghost. But hold on. If gravity has a speed, you run into a problem that nearly derailed the entire idea, a problem that a French mathematician identified in 1805, a problem so convincing that it seemed to prove gravity must be virtually instantaneous. And the man who identified it was arguably the greatest applied mathematician who ever lived. Pierre-Simon Laplace was born in 1749 in Normandy, France, to a family of modest means. By the time he was 30, he had essentially invented the mathematical framework for understanding the stability of the solar system. His 5-volume masterwork, The Traité de mécanique céleste, published between 1799 and 1825, did for celestial mechanics what Newton's Principia had done for gravity itself. It translated the messy, complicated motions of the real solar system into precise mathematical language. Laplace could calculate the gravitational interactions between Jupiter and Saturn, predict the precession of orbits, and demonstrate that the solar system was stable over millions of years. He was so confident in the completeness of his mathematical universe that when Napoleon reportedly asked him why his book never mentioned God, Laplace replied, "I had no need of that hypothesis." And Laplace was the first person to seriously attack the question of gravity's speed with mathematics. His argument was elegant and, on the surface, devastating. It went like this. If gravity takes time to travel from the sun to a planet, then the planet is always being pulled toward where the sun was, not where the sun is. The sun is moving too, orbiting the center of the galaxy, moving through space. If the gravitational signal takes time to arrive, the force would point slightly behind the sun's current position, like rain that appears to fall at an angle when you walk through it. This effect is called aberration, and it is very real for light. Light from a star appears to come from a slightly different direction, depending on Earth's velocity, an effect first measured by James Bradley in 1728. Now here is where Laplace's argument gets really interesting. If gravity aberrates the way light does, the slight misdirection of the gravitational force would add a tiny tangential push to every orbit. Think of it like someone pulling you on a leash, but always pulling toward where they were a moment ago, rather than where they are now. That small angular offset would inject energy into orbits, causing them to spiral outward. The closer the planet and the faster it moves, the bigger the effect. Laplace calculated how fast gravity would need to travel to be consistent with the observed stability of the Moon's orbit. His answer was staggering. Gravity would have to propagate at least 7 million times the speed of light. Not 7 times, not 7,000 times, 7 million times. And that essentially ruled out any finite speed for gravity. If gravity needed to be that fast to avoid destabilizing the Moon's orbit, it might as well be instantaneous. This result stood for a century. It was so compelling that when Einstein began developing general relativity in 1907, Laplace's argument was still considered a serious obstacle. If gravity travels at the speed of light, as Einstein's equations predicted, then how can the solar system be stable? Laplace had shown, apparently rigorously, that light-speed gravity would tear orbits apart. But Laplace was wrong. Not about the math. The math was correct. He was wrong about the physics. He had applied the concept of finite propagation speed to a purely Newtonian framework, a theory that was not designed to handle it. And the reason his argument fails in Einstein's framework is so subtle and so beautiful that it would take another century to fully appreciate. The key insight, published by the physicist Steve Carlip in 2000, is that general relativity contains velocity-dependent terms that almost perfectly cancel the aberration effect. In Newtonian gravity, if you give the force a travel time, you get aberration, and the aberration destabilizes orbits. But general relativity is not Newtonian gravity with a speed limit bolted on. It is a fundamentally different theory. In general relativity, a moving mass generates additional gravitational effects beyond the simple inverse square pull. These effects, analogous to the magnetic field generated by a moving electric charge, create corrections that almost exactly compensate for the travel time delay. The force ends up pointing very nearly at the sun's current position, not its retarded position, even though the gravitational signal has been traveling at a finite speed. This cancellation is not a coincidence. It is required by the mathematical structure of the theory. It is a consequence of Lorentz invariance, the fundamental symmetry that says the laws of physics must look the same, regardless of how fast you are moving. The residual aberration effect that survives the cancellation is tiny, proportional to the square of the velocity divided by the speed of light squared, rather than the first power that Laplace calculated. For Earth, that means the actual orbital perturbation from gravity's finite speed is about 100 billion times smaller than what Laplace predicted. So Laplace asked exactly the right question. He used exactly the right mathematical technique. He got a result that was logically impeccable within his theoretical framework. And he was wrong, because the correct framework had not been invented yet. He was trying to analyze a Lamborghini using the blueprints of a horse-drawn carriage. But notice something important. We still have not answered the central question. We have learned that gravity is not instantaneous, because Einstein's theory says so, and Laplace's objection has been resolved. But we have not actually measured the speed of gravity. We have a prediction. We do not yet have a measurement. The prediction could be wrong. Einstein himself would come to doubt it. On a day in 1907 that he would later describe with extraordinary precision, Albert Einstein was sitting in a chair in the patent office in Bern, Switzerland, when a thought struck him. He called it the happiest thought of his life. The thought was this: a person falling freely does not feel their own weight. If you jumped off a building, and we are ignoring air resistance here, and please do not actually test this, you would feel weightless during the fall. Everything in your pockets would float beside you. A ball released from your hand would not fall to the floor, it would hover. Inside your little falling laboratory, gravity has effectively vanished. This sounds trivial. It is not. What Einstein realized is that this means gravity and acceleration are fundamentally the same thing. If you are in a closed room with no windows, there is no experiment you can perform that will tell you whether you are standing on the surface of a planet or accelerating through empty space at the same rate. The two situations produce identical physics. This is the equivalence principle, and it would become the cornerstone of general relativity. It would also take him 8 years to turn it into a finished theory, and those 8 years nearly destroyed him. Einstein spent the period from 1907 to 1915 teaching himself the mathematics of curved spaces, a subject called differential geometry that had been developed decades earlier by Bernhard Riemann and others. He made false starts. He published incorrect equations. He collaborated with his friend Marcel Grossmann, who was better at the math. And even with Grossmann's help, he went down dead ends that cost him months. By 1913, he had a theory that was almost right, but not quite, and he convinced himself, it was correct. It was not. He spent the next 2 years slowly realizing his mistake and racing to fix it, all while the German mathematician David Hilbert was working on the same problem and converging on the same answer. In November 1915, Einstein presented the correct field equations over a series of 4 lectures to the Prussian Academy of Sciences. The final version was presented on November 25th. He later told friends that he was so excited by the result that he could not sleep for days and that he had heart palpitations. The first thing Einstein did with his new equations was calculate the orbit of Mercury. This was not random. Mercury's orbit had been a thorn in the side of Newtonian gravity for decades. The planet's perihelion, the point of closest approach to the Sun, precesses slowly around the Sun over time. Newton's theory predicted most of this precession from the gravitational influence of the other planets, but there was an unexplained residual of 43 arc-seconds per century. 43 arc-seconds is a tiny angle, about 1/84th of a degree per century, but it was persistent, reproducible, and unexplained. Astronomers had been measuring it since Urbain Le Verrier first identified the discrepancy in 1859. Some proposed a hidden planet, which they named Vulcan, orbiting closer to the Sun. It was never found because it does not exist. The explanation was not a missing planet, it was a missing theory. Einstein's field equations, applied to Mercury's orbit, predicted an additional precession of exactly 43 arcseconds per century. No adjustments, no free parameters. The theory simply produced the right number. Einstein later said this was the moment he knew general relativity was correct. Not when the solar eclipse expedition of 1919 confirmed the bending of starlight, which made him famous. The Mercury calculation, done in November 1915, weeks before the theory was even published. That was when he knew. But the equivalence principle had a problem that Einstein recognized immediately, and that would consume those 8 years of his life. If gravity and acceleration are the same, then gravity cannot be a force in the traditional sense. Forces act differently on different objects depending on their mass. A heavy box requires more force to push than a light one. But gravity does not work this way. Drop a bowling ball and a feather in a vacuum, and they fall at exactly the same rate. Galileo is supposed to have demonstrated this from the Leaning Tower of Pisa in 1589. Though the story is probably apocryphal, the Apollo 15 astronauts demonstrated it on the Moon in 1971, dropping a hammer and a feather in the lunar vacuum. They hit the ground simultaneously. This is strange. It means gravity does not care what you are made of. It does not care how heavy you are. It pulls everything the same way. And the only way Einstein could make sense of this was to stop thinking of gravity as a force altogether and start thinking of it as geometry. Gravity is not pulling you toward the Earth. The Earth is curving the space around it, and you are following the straightest possible path through that curved space. What you experience as the force of gravity is actually the curvature of spacetime itself. This reconceptualization is not just philosophical window dressing. It completely changes what it means for the Sun to disappear. In Newton's framework, the Sun exerts a force across empty space, and the question is how fast that force propagates. In Einstein's framework, the Sun curves the space-time around it, creating a kind of bowl shape that Earth rolls around in. If the Sun vanishes, the question becomes something different and much more interesting. How fast does the curvature of space-time change? How quickly does the bowl flatten out? Einstein's field equations, which he presented in their final form on November 25, 1915, predict that changes in the curvature of space-time propagate at exactly the speed of light. Not approximately, not roughly, exactly. The speed of gravity and the speed of light are the same. And this is not a coincidence. It is a structural consequence of the theory. Both light and gravity are constrained by the same geometric property of space-time. Nothing that carries information can travel faster than c 300 million meters per second, and gravitational influence is information. This means that when the Sun vanishes in our thought experiment, a spherical shell of altered space-time expands outward at the speed of light, like the surface of an inflating balloon. Inside the shell, space-time is flat, vacuum, no curvature. Outside the shell, space-time is still curved, still shaped by the Sun's mass, as if nothing has happened. The shell sweeps past Mercury after about 3 minutes and 12 seconds. It reaches Earth after 8 minutes and 19 seconds. Until that shell arrives, we continue orbiting normally because the space-time around us is still curved. We are not orbiting a memory or a ghost. We are moving through a space-time geometry that genuinely, physically, still exists. The sun is already gone, but the curvature it left behind is real, and it persists until the information about the sun's absence arrives. And when the sun reappears 1 second later, a second shell expands outward, restoring the curvature. The 1 second gap between the two shells is what produces our 3 millimeter deviation. For exactly 1 second, as measured at the sun, Earth's local space-time goes flat, and Earth travels in a straight line. Then the curvature returns, and the orbit resumes, shifted by an amount too small to measure. But here is where Einstein's story takes a turn that almost nobody expects. Having predicted that changes in space-time curvature propagate as waves, Einstein proceeded to spend the next 2 decades going back and forth on whether those waves were real. In 1916, just months after completing general relativity, Einstein published a paper predicting the existence of gravitational waves. These would be ripples in space-time itself, propagating at the speed of light generated by accelerating masses. Every orbiting planet, every spinning star, every pair of objects dancing around each other should produce them. The idea followed naturally from the field equations. If electromagnetism produces electromagnetic waves when charges accelerate, and if gravity is a field theory with similar mathematical structure, then gravity should produce gravitational waves when masses accelerate. But there was a problem. The waves were fantastically weak. Einstein calculated that the gravitational waves produced by the Earth orbiting the Sun would carry a power of about 200 watts. 200 watts. That is roughly the output of 2 household light bulbs. The entire orbital energy of the Earth-Sun system, radiating gravitational waves at the power of 2 light bulbs. At that rate, it would take far longer than the current age of the universe for Earth's orbit to decay by any measurable amount. The waves were real in theory, but they seemed permanently beyond detection. And then Einstein made a mistake that nearly erased gravitational waves from physics entirely. In 1936, Einstein and his collaborator Nathan Rosen wrote a paper with a startling conclusion. Gravitational waves do not exist. They had analyzed a specific class of wave solutions and found a mathematical singularity, a point where the equations blew up to infinity, which they interpreted as proof that the waves were unphysical. The paper was titled, quite straightforwardly, "Do gravitational waves exist?" And the answer Einstein and Rosen gave was no. They submitted the paper to the Physical Review, where the editor, John Tate, sent it out for anonymous peer review. Einstein had never encountered this practice before. In Europe, journal editors made decisions themselves. The referee, whose identity would not be confirmed for decades, was a physicist named Howard Percy Robertson. He was thorough. He wrote a 10-page critique identifying the precise error in Einstein's reasoning. The singularity Einstein and Rosen had found was a coordinate artifact, an illusion created by their choice of mathematical coordinates, not a real physical problem. Change the coordinate system, and the singularity vanishes. The waves are fine. Einstein was furious. He wrote an angry letter to the editor declaring that he had not submitted the paper to be reviewed by anonymous critics, and he withdrew it. He never submitted to the physical review again, but the story does not end there. Robertson happened to be at Princeton, and he happened to know Einstein's new assistant, a Polish physicist named Leopold Infeld. Robertson explained the error to Infeld over a series of conversations, and Infeld carefully, diplomatically, explained it to Einstein. To his credit, Einstein recognized the mistake. The paper was revised to describe cylindrical gravitational waves, which do exist, and published in the Journal of the Franklin Institute in 1937. The title was changed. The conclusion was reversed. Gravitational waves survived, but the damage lingered. If Einstein himself had doubted their existence, if the greatest physicist alive had nearly convinced the world they were a mathematical mirage, how confident could anyone be? The debate simmered for another 2 decades. It was not until 1957 that the physicist Richard Feynman, at a conference in Chapel Hill, North Carolina, presented what became known as the sticky bead argument. Imagine 2 beads threaded on a sticky rod, Feynman said. If a gravitational wave passes through, it will push the beads along the rod. The friction between the beads and the rod will generate heat. Heat is energy. Energy is real. Therefore, the wave is real. It carries energy. It can do work. It is not just a mathematical artifact. The argument was simple enough to fit on a napkin, and it essentially settled the theoretical question. Gravitational waves are real. They carry energy, and they propagate at the speed of light. But settling the theoretical question and actually detecting the waves were 2 entirely different problems. Nobody had any idea how to build a detector sensitive enough. The waves stretch and compress space by absurdly tiny amounts, roughly 1 part in 10 to the 21st, for the kinds of astrophysical sources that might be detectable. That means if you had a rod a meter long, a passing gravitational wave from a distant source would change its length by about 1/1,000,000th of the width of a proton. How do you measure that? In 1969, a physicist at the University of Maryland named Joseph Weber claimed he had. He built a pair of aluminum cylinders, each about 2 meters long and 1 meter in diameter, equipped with piezoelectric sensors to detect tiny vibrations. He called them resonant bar detectors. If a gravitational wave passed through, it would make the bar ring like a bell, and the sensors would pick up the vibration. Weber announced that he was detecting gravitational waves regularly. The physics world was electrified, but other groups built their own bars, and none of them detected anything. The signals Weber claimed to see were hundreds of times stronger than any theoretical prediction, and they seemed to come preferentially from the center of the Milky Way at a rate that, if real, would mean the galaxy was radiating itself out of existence. By the mid-1970s, the consensus was clear. Weber's detections were not real. Something was wrong with his analysis, though to this day nobody is entirely sure what. Weber spent the rest of his career defending his results, growing increasingly isolated. He died in 2000, never having accepted that his detections were spurious. But Weber's failure was not the end of the story. It was the beginning, because his experiment, even though it produced the wrong answer, established gravitational wave detection as a real field of experimental physics. Before Weber, detecting gravitational waves was a dream. After Weber, it was a challenge, and challenges attract ambitious people. Two of those people were already at work while Weber was publishing his disputed results. One was at MIT. The other was at Caltech. They did not know each other yet, and they had very different personalities, but they would end up building the most sensitive scientific instrument in human history. Rainer Weiss was born in Berlin in 1932. His family fled the Nazis when he was a boy, first to Prague, then eventually to New York. He grew up in the Washington Heights neighborhood of Manhattan, a pocket of German Jewish refugees. As a student at MIT, he dropped out, went back, dropped out again, and eventually earned his PhD in physics. He had a reputation as a brilliant experimentalist with a talent for electronics and a deep suspicion of theoretical hand-waving. He wanted to measure things, not speculate about them. In the early 1970s, Weiss was teaching a course on general relativity at MIT, which he felt was a stretch for an experimentalist. When it came time to discuss gravitational wave detection, he wanted to give his students something concrete, so he sat down and worked out, from first principles, exactly what a gravitational wave would do to a beam of light bouncing between mirrors. The result was a 22-page document published in MIT's Quarterly Progress Report in 1972 that laid out the complete blueprint for what would become LIGO. Not roughly, completely, Weiss identified every major source of noise that would plague the detector: seismic vibration, thermal fluctuations, photon shot noise, residual gas molecules, and calculated the sensitivity that would be needed to detect astrophysical sources. He concluded that you would need arms several kilometers long. This was not a theoretical fantasy. This was an engineering document. It was a recipe, and it was largely ignored for years. Meanwhile, at Caltech, Kip Thorne was approaching the problem from the opposite direction. Thorne was a theorist, a student of the great John Archibald Wheeler, and one of the world's leading experts on general relativity. In 1968, he had visited Moscow and met the Soviet physicists who were building their own gravitational wave detectors. He returned to Caltech, convinced that gravitational wave astronomy would be the next great frontier. But unlike Weiss, Thorne was not an experimentalist. He could predict what the waves would look like, but could not build a detector. What he could do was calculate with extraordinary precision the gravitational wave signals that merging black holes and neutron stars would produce. These templates, the predicted shapes of the signals, would turn out to be essential. Without knowing exactly what you are looking for, finding a signal 1,000th the width of a proton in a sea of noise is impossible. Weiss and Thorne met in 1975, and the partnership, though frequently contentious, became the foundation of LIGO. But the project nearly died a dozen times before it succeeded. The scale of what they were proposing was unprecedented for physics. 2 L-shaped detectors, each with arms 4 kilometers long, filled with the most perfect vacuum on Earth, using lasers bouncing between the most perfectly shaped mirrors ever made, measuring a distance change smaller than any distance change ever measured before. The cost would eventually reach over $1 billion. The National Science Foundation funded a series of prototypes through the 1980s, but progress was slow and the political challenges were enormous. Physicists questioned whether the project could work. Administrators questioned whether the cost was justified for a measurement that might never succeed. The project director was replaced. Morale collapsed. Enter Barry Barish. In 1994, Barish became LIGO's principal investigator, and he brought something the project desperately needed: organization. Barish was a particle physicist, accustomed to the massive international collaborations of high-energy physics. He restructured LIGO as a proper big science project with clear management, international partnerships, and a phased upgrade plan. The original LIGO detectors, which began operating in 2002, were never expected to detect anything. They were proof of concept. The real instrument would be advanced LIGO, an upgrade that would improve sensitivity by a factor of 10, increasing the volume of space that could be searched by a factor of 1,000. Advanced LIGO began its first official observing run on September 18, 2015. The instrument was so sensitive that it could detect a change in the length of its 4-kilometer arms, equivalent to 1/10,000th the diameter of a proton. If you scaled up LIGO's arms to the distance from Earth to the nearest star, 4.24 light-years, the measurement it performs would be equivalent to detecting a change of less than the width of a human hair. But the universe did not wait for the official start date. 3 days earlier, on September 14th, at 5:50 in the morning Eastern Time, during an engineering run while the detectors were being calibrated, a signal arrived. The signal was a chirp. It started low, around 35 Hz, and swept upward in frequency and amplitude over about 0.2 of a second, reaching 250 Hz before cutting off abruptly. If you converted it to sound, it would sound like a quick whoop, rising in pitch. That whoop was the sound of 2 black holes, one 36 times the mass of the Sun and one 29 times the mass of the Sun, spiraling into each other and merging into a single black hole of 62 solar masses, 1.3 billion light-years away. 3 solar masses of material, about 6 million trillion kilograms, had been converted entirely into gravitational wave energy in a fraction of a second. The peak power output for that brief instant was 3.6 times 10 to the 49th watts. That is roughly 50 times the combined luminosity of every star in the observable universe. All of that energy went into shaking the fabric of space-time itself. By the time those ripples reached Earth, after traveling for 1.3 billion years, they had weakened to a strain of about 1 times 10 to the minus 21. That means they stretched LIGO's 4-kilometer arms by about 4 times 10 to the minus 18 meters. 4 atometers. 1,000th the diameter of a proton. The detection team was initially skeptical. LIGO had a practice of injecting fake signals into the data stream to test the analysis pipeline, and many of the scientists assumed this was one of those blind injections. It took weeks to confirm that no injection had been made. The signal was real. The statistical significance was 5.1 sigma, meaning the probability of the signal being a random noise fluctuation was less than 1 in 3.5 million. The false alarm rate was calculated as less than 1 event per 203,000 years of observation. The discovery was announced on February 11th, 2016. The date was not a coincidence. It was almost exactly 100 years after Einstein had first predicted gravitational waves in 1916. Rainer Weiss, Kip Thorne, and Barry Barish received the Nobel Prize in Physics in 2017. But here is the thing. GW150914 proved that gravitational waves exist. It proved that black holes merge. It proved that LIGO works. What it did not prove, at least not directly, is that gravity travels at the speed of light. The signal came from two black holes, and black holes do not emit light. There was no electromagnetic counterpart, no flash, no gamma ray burst, nothing to compare the arrival time against. LIGO had heard the space-time ripples, but there was no second messenger to check against. To nail down the speed of gravity, you needed something rare. You needed a gravitational wave source that also produces light. You needed both messengers from the same event, arriving close enough together that you could compare their travel times. You needed a neutron star merger. And on August 17th, 2017, you got one. The signal was designated GW170817, following the naming convention that uses the date of detection. At 12:41 UTC, the LIGO detector in Hanford, Washington, and the LIGO detector in Livingston, Louisiana, along with the Virgo detector near Pisa, Italy, picked up a gravitational wave signal that was different from anything they had seen before. The black hole mergers had been quick, lasting a fraction of a second at detectable frequencies. This signal lasted about 100 seconds. It was a long, slow inspiral, building in frequency, like a record speeding up on a turntable. The frequency told them what was spiraling. Black holes are heavy and merge fast. This was lighter. This was slower. These were neutron stars. Neutron stars are what is left behind when a massive star runs out of fuel and its core collapses. They are about 12 kilometers across, roughly the width of a city, but they contain more mass than the Sun. A teaspoon of neutron star material weighs about 6 billion tons. These two neutron stars had been orbiting each other for billions of years, their orbits decaying slowly as gravitational waves carried away energy, spiraling closer and closer, moving faster and faster until this moment. The final 100 seconds, 1.74 seconds after the gravitational wave signal ended, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same part of the sky. 1.74 seconds. Light and gravity arriving from the same cataclysmic event, 130 million light-years away, separated by less than 2 seconds. What happened next was unprecedented in the history of astronomy. Within hours, alerts went out to observatories around the world. About 4,000 astronomers at roughly 70 observatories on every continent and in orbit pointed their instruments at the same patch of sky in the constellation Hydra. They found the source, a galaxy called NGC 4993, 130 million light-years away. And in that galaxy, they watched something no human had ever seen before, a kilonova. When the two neutron stars collided, the impact was so violent that it ejected a cloud of incredibly hot, neutron-rich material into space at a significant fraction of the speed of light. In that cloud, a process called rapid neutron capture, or the RR process, was synthesizing heavy elements: gold, platinum, uranium, all of the elements heavier than iron that cannot be forged in the cores of ordinary stars. This single collision produced roughly 16,000 Earth masses of heavy elements. About 10 Earth masses of that was gold and platinum. 10 Earths made of gold, created in a fraction of a second by two dead stars. that had been spiraling toward this moment for billions of years. The kilonova glowed for weeks, changing color as the radioactive heavy elements decayed. It went from blue to red as the ejector expanded and cooled. For the first time, astronomers were watching the cosmic forge that produces the heaviest elements in the universe. The gold in your wedding ring, the platinum in a catalytic converter, the uranium in a reactor. All of it was made in events like this one, billions of years ago, scattered into interstellar space and eventually swept up into the cloud of gas and dust that became our solar system. But for our story, the critical measurement was the timing. Now think about what that means. These two signals, one carried by the ripples of spacetime itself and the other carried by electromagnetic radiation, had been traveling across the universe for approximately 130 million years. They left their source at essentially the same moment, the moment two neutron stars collided and simultaneously shook spacetime and produced a burst of gamma radiation. And after crossing 4 times 10 to the 24th meters of space, roughly 400,000 trillion meters, they arrived at Earth within 1.74 seconds of each other. The 1.74 second difference does not mean gravity is slightly slower than light. Astrophysicists expected a delay of this size because the gamma rays are not produced at the exact instant of merger. They are produced by a relativistic jet of material that forms in the aftermath, which takes a brief but measurable amount of time to launch and break through the surrounding debris. The gravitational waves come from the inspiral and merger itself. The gamma rays come from the jet that forms slightly later, so the small delay is a production delay at the source, not a propagation delay in transit. When physicists accounted for this, the result was one of the most precise measurements in the history of science. The difference between the speed of gravity and the speed of light after traveling 130 million light years is constrained to be less than 3 parts in 10 to the 15th. That is 15 decimal places of agreement. The speed of gravity equals the speed of light to within plus or minus 0.000000000000003%. Laplace had said gravity must travel at least 7 million times the speed of light. Einstein said it travels at exactly the speed of light. 130 million light years of cosmic travel time settled the argument. Einstein was right. Newton's instantaneous gravity was wrong. Laplace's objection, though brilliant, was based on an incomplete theory. The speed of gravity is c, not approximately c, not close to c. It is c. And this brings us back to our 1 second disappearance, because now we know with 15 decimal places of precision exactly how long it takes for Earth to learn that the Sun is gone. The Sun is 149.6 million kilometers away. Light covers that distance in 499.005 seconds. That is 8 minutes and 19 seconds. And gravity covers it in the same time, because gravity and light travel at the same speed for the same reason, constrained by the same geometry of space-time. For 8 minutes and 19 seconds after the Sun vanishes, absolutely nothing changes on Earth. Nothing. Not the orbit, not the light, not the temperature, not anything. We are orbiting a sun that no longer exists, warmed by light that was emitted before the disappearance, held on course by space-time curvature that has not yet had time to flatten, and we have no way to know. No instrument can detect the change before the information arrives, because no information of any kind can travel faster than light. Then, 8 minutes and 19 seconds in, the gravitational and luminous effects of the disappearance arrive simultaneously. For exactly 1 second, Earth is in flat spacetime. The pull toward where the Sun was drops to zero. Earth drifts 3 millimeters off its orbital path, and then, 1 second later, the restoration signal arrives, spacetime recurves, and the orbit resumes. But what about the light? This is where something genuinely weird happens, and it is one of the most commonly botched details in popular treatments of this thought experiment. Most descriptions imagine the Sun blinking off like a light switch. One instant it is there, blazing at full brightness. The next instant, total darkness. Then, 1 second later, it snaps back on. That is not what would happen. The Sun is not a point source of light. It is an extended object, roughly 1.4 million kilometers across. Light from the near edge of the Sun's disk takes about 2.3 seconds less to reach you than light from the far edge, because the far edge is physically farther away. When you look at the Sun at any given instant, what you are actually seeing is a composite image assembled from photons that left different parts of the solar surface at slightly different times. The center of the disk is closer to you than the limbs. The photons are arriving from a range of distances, and therefore a range of travel times. This means the 1 second disappearance does not produce a 1 second blackout. It produces a gradual dimming that lasts longer than 1 second and never reaches total darkness. Here is how it works. Imagine the Sun vanishes at time zero, as measured at the Sun itself. The first photons to stop arriving at Earth are the ones from the nearest point on the Sun's surface, the sub-Earth point, the spot on the Sun closest to you. Those were the last photons emitted before the disappearance, and they have the shortest travel time. As time progresses, the missing photons spread outward from the center of the solar disk toward the limbs, like a shadow eating inward, or more precisely, like a hole opening up from the center outward, because the Sun's edge is farther away, and those photons are still arriving. After about 1.16 seconds, photons from the entire near hemisphere of the Sun have stopped arriving. The disk would appear as a bright ring with a dark center, a kind of anti-eclipse, with the dark region growing outward. After about 2.3 seconds, photons from the farthest visible limb of the Sun stop arriving. Now the entire disk is dark, but the Sun only disappears for 1 second. So add time equals 1 second. As measured at the Sun, it reappears. The restoration photons begin arriving, starting again from the center of the disk, just as the disappearance was still eating outward toward the limbs. The darkening and the brightening overlap. The net result is a smooth, partial dimming. The total event, from first detectable darkening to full brightness restored, lasts approximately 3.3 seconds as seen from Earth. The maximum darkening, which occurs when the disappearance signal has reached the center, but the restoration signal has not yet begun arriving, blocks roughly 68% of the Sun's light. Not 100%, 68%. You would never see a fully dark Sun if you happened to be looking at the Sun at that moment, and if your eyes could somehow respond fast enough, you would see something like a rapid, deep pulse of dimming, like someone briefly turning down a dimmer switch to about a third brightness and then turning it back up. The whole thing would take about 3 seconds. On a day with scattered clouds, you probably would not notice. It would look like a cloud passing over the sun, but faster than any cloud. Here is what you would not see. You would not see stars appear. Daytime stars become visible during a total solar eclipse because the sky darkens enough for your eyes to adapt. But that adaptation takes tens of seconds. A 3-second partial dimming would not give your eyes time to adapt, and the remaining 32% of sunlight that still reaches you at peak dimming is more than enough to wash out the stars. You would not see the corona, the sun's outer atmosphere that becomes visible during total eclipses, because the sun never fully disappears from your perspective. You would not see the landscape plunge into darkness. On a sunny day, the illumination would drop from about 100,000 lux to about 32,000 lux for a couple of seconds. 32,000 lux is still brighter than an overcast day, which is typically around 10 to 20,000 lux. If you were indoors and not looking out a window, you might not notice anything at all. If you were outdoors, you might feel a brief shadow pass over, the way a fast-moving cloud does in windy weather, and by the time you looked up, it would be over. Solar panel output would dip briefly. Automatic lighting systems with fast response times might flicker on and then off. High-speed photometric instruments, if anyone happened to be pointing one at the sun at that exact moment, would record a beautiful and inexplicable dip in the solar flux curve. But no human being going about their day would have any reason to think the sun had just ceased to exist. The energy missing from this 3.3-second partial dimming is real. Earth intercepts about 1/2 billionth of the sun's total output, which works out to 1.74 times 10 to the 17 watts. Over the effective interruption, accounting for the partial dimming profile, Earth misses about 1.22 times 10 to the 17 joules of absorbed solar energy after factoring in Earth's albedo. That is roughly the energy of 0.83 Tsar bomber detonations. Not trivial in absolute terms, but the thermal mass of the Earth makes it completely unnoticeable. The atmosphere alone has a mass of 5.15 times 10 to the 18 kilograms and a heat capacity that can absorb enormous amounts of energy with barely any temperature change. The missing solar energy would produce a temperature drop of about 24 millionths of a degree Celsius if you include the ocean mixed layer, which is the relevant thermal reservoir on short timescales. The temperature change drops to less than 1 millionth of a degree. The most sensitive thermometers on Earth have a resolution of about 1/10,000th of a degree. This is 100 times below their threshold. What about the ionosphere, the layer of charged particles in the upper atmosphere that is directly maintained by solar ultraviolet radiation? The ionosphere is the one part of the atmosphere that responds relatively quickly to changes in solar input. During a total solar eclipse, the ionospheric D region, the lowest layer at about 60 to 90 kilometers altitude, begins to fade within minutes. As the sunlight is progressively blocked, measurements during the August 2017 eclipse showed that electron density in the D region dropped by about 40% over a 30-minute period as the moon's shadow crossed. But that response requires a sustained interruption. The D region responds on a timescale of minutes. The F2 region, the highest and densest ionospheric layer, responds on a timescale of hours. A 3.3-second partial dimming would produce no measurable ionospheric response whatsoever. The free electrons in the ionosphere would not even begin to recombine before the sunlight returned. Biological effects are similarly non-existent. Global photosynthesis fixes about 3,800 tons of carbon per second. A 1-second interruption would mean about 3.8 kilotons of carbon not fixed, roughly 3 billionths of 1% of annual photosynthesis. Plants would not respond. Animals would not respond. The eclipse behaviors that birds and insects exhibit, the ones where crickets start chirping and roosters crow, those require the slow, progressive dimming of a real eclipse, which takes about 30 minutes. A 3-second flicker would be over before any biological system could even register the change in light levels. So the practical effects are, from any human perspective, zero. The orbit shifts by 3 millimeters. The temperature drops by an amount 100 times smaller than any thermometer can measure. The light dims by 2/3 for 3 seconds. No living thing notices. But the physical effects are not really the interesting part. The interesting part is what the thought experiment forces you to confront about the nature of reality. Because every calculation we just did, every number, every prediction depends on the assumption that the sun can vanish. And it cannot. Not even for a second. Not even in principle. This is the point in the video where we need to stop treating this as a fun what-if question and start taking the physics seriously. Because general relativity does not just predict what would happen if the sun disappeared. It says the sun cannot disappear. The theory forbids it. The reason is conservation of energy and momentum, but not the simple textbook version you learned in high school. In general relativity, conservation is not an extra rule imposed on top of the theory. It is built into the geometry. It is a mathematical consequence of the structure of spacetime itself. Einstein's field equations describe the relationship between the distribution of mass and energy, represented by something called the stress-energy tensor, and the curvature of spacetime, represented by the Einstein tensor. The stress-energy tensor, which physicists write as T mu nu, satisfies a condition called covariant conservation. The covariant divergence of T mu nu equals 0. This is not something Einstein assumed. It is something the equations require. It falls out of a mathematical identity called the Bianchi identities, which are properties of curved spaces that were known before Einstein even started working on gravity. What covariant conservation means, in plain language, is that energy and momentum cannot appear or disappear spontaneously. They can change form. They can move from one place to another. Mass can become radiation. Kinetic energy can become heat. But the total, properly measured in the framework of general relativity, is conserved. The sun's mass is a form of energy. Roughly 99.86% of the total mass of the solar system is in the sun. That mass energy is not allowed to simply vanish from the equations. There is no mathematical operation you can perform on the stress-energy tensor that sets the sun's contribution to 0 without breaking the conservation law that the theory's own geometry demands. Now you might think, well, this is a thought experiment. We are imagining breaking the rules to see what happens. And that is fair in a Newtonian framework, where the rules are simple enough that you can turn individual ones off and see what changes. But general relativity is different. The rules are not independent. They are interconnected. The conservation law and the field equations and the structure of space-time are all the same thing. You cannot violate one without the others becoming inconsistent. If you remove the sun's mass from the stress-energy tensor, the field equations no longer have a valid solution. The geometry of space-time becomes mathematically undefined. It is not that something dramatic would happen. It is that the equations cannot tell you what would happen because they no longer make sense. There is another way to see this, which is more intuitive. It is called Birkhoff's theorem, and it was proven independently by the Norwegian physicist Bjørn Jebsen in 1921 and the American mathematician George Birkhoff in 1923. The theorem states that the spacetime outside a spherically symmetric mass distribution must be the Schwarzschild solution, and that this solution is static. It does not change with time. It does not depend on what the mass is doing inside the spherical boundary, as long as the total mass stays the same and the distribution remains spherically symmetric. This means that if the Sun were to somehow rearrange its internal structure, compress, expand, pulsate, whatever, the gravitational field outside would not change at all, provided the total mass and the spherical symmetry are maintained. The only way to change the external field is to change the total mass or break the symmetry. And the only way to change the total mass is to send something outward through the spherical boundary, which takes time and which propagates at or below the speed of light. Birkhoff's theorem is actually the deep reason why the Sun's 1 second disappearance, if it could happen, would propagate outward as a spherical shell at the speed of light. It is also the reason the thought experiment does not produce gravitational waves in the traditional sense. A common misconception about this scenario is that the Sun vanishing and reappearing would send out a burst of gravitational waves like a cosmic ping. But gravitational waves require a specific type of asymmetry. Einstein showed in 1918 that gravitational radiation is produced by time-varying quadrupole moments. That is, you need a mass distribution that is not just changing, but changing in a way that is not spherically symmetric. A pulsating sphere does not radiate gravitational waves. Two objects orbiting each other do. A bar spinning end over end does. But a mass that appears or disappears spherically does not. So our vanishing Sun would produce a spherically expanding step function in the curvature of spacetime, a sudden transition from curved to flat expanding outward at sea, not an oscillating wave. LIGO would not detect it as a gravitational wave signal. The effect on each planet would be a sudden cessation of gravitational acceleration, lasting 1 second, followed by a sudden resumption. But the word sudden is doing a lot of work there, because the transition arrives at the speed of light, and from the perspective of any given point, it is indeed abrupt. The equivalence principle adds one more layer. In a freely falling reference frame, gravity is locally undetectable. Einstein's happiest thought. If you are falling freely around the Sun, which is what orbiting is, you do not feel the Sun's gravity. You feel weightless. You feel exactly the way you would feel floating in deep space with no massive objects nearby. This means that when the sun's gravitational influence disappears for 1 second, nothing about your local experience changes. You were weightless before while orbiting, and you are weightless during while drifting in a straight line. The 3 mm deviation is real, but it is not something you could feel or detect locally without an external reference point. So here is the complete physical picture. The sun vanishes. A spherical shell of flat spacetime expands outward at sea. It reaches Earth after 8 minutes and 19 seconds. For 1 second, Earth is in flat spacetime and moves in a straight line, deviating 3 mm from its orbital path. The light dims partially over about 3.3 seconds, reaching a maximum dimming of 68% before recovering. The temperature drops by 24 millionths of a degree. The ionosphere does not respond. Biology does not respond. No human notices anything. Then the sun returns. A second spherical shell restores the curvature. The orbit resumes with a permanent but unmeasurably small change in eccentricity, and Earth continues as if nothing happened. Because from any practical standpoint, nothing did. 3 mm, 24 millionths of a degree, a 3-second flicker that never reaches total darkness. That is the entire physical effect of the sun ceasing to exist for 1 full second. The Earth does not fly off into space. The oceans do not freeze. People do not stumble around in pitch darkness. Every dramatic version of this scenario you have ever seen described online is wrong. But the thought experiment was never really about what happens to Earth. It was about what happens to gravity. And what we learned across 3 centuries of investigation is that gravity is not a force that reaches across empty space. It is not an invisible rope. It is not instantaneous. It is the shape of space-time itself, and changes to that shape propagate at exactly the speed of light. Because light speed is not really about light at all. It is the speed limit of causality. It is the fastest rate at which any event can influence any other event, the maximum speed of information itself. Newton discovered this problem. He described gravity's effects with perfect precision, but called the mechanism absurd because he could not explain how a force could act across a void. Laplace tried to measure the speed of that mechanism and concluded it must be nearly infinite because his mathematical framework did not contain the corrections that would later resolve the apparent contradiction. Einstein reconceived the entire problem, replacing force with geometry, and predicted that gravitational changes propagate at sea. He then spent 20 years wavering on whether the waves those changes produce are real. Feynman settled the theoretical question with a thought experiment about beads on a sticky rod. Weber tried to detect the waves and failed. Weiss designed the machine that could actually do it. Thorne predicted what the signals would look like. Barish organized 1,000 scientists to build the thing. And on a September morning in 2015, 1.3 billion years after 2 black holes collided, the signal arrived at a detector that had not yet officially been turned on. 2 years later, 2 neutron stars collided 130 million light-years away. And for the first time in history, humanity heard the same event in both gravity and light. The 2 signals, after crossing a distance that would take you 4 trillion years to drive at highway speed, arrived within 1.74 seconds of each other. The speed of gravity equals the speed of light to 15 decimal places. And that should be the end of the story. We asked how gravity crosses empty space. The answer is that it does not cross it. It is the shape of that space. Changes in mass change the shape, and the new shape propagates outward at c. We measured it. Case closed. Except it is not closed, because the 15 decimal places of precision we just celebrated conceals something uncomfortable. We measured the speed of gravitational waves. We did not explain why gravity has a speed at all. We did not explain what space-time curvature actually is. We replaced Newton's absurd force with Einstein's geometry. But geometry is just a description. Space-time bends, we say. But what is bending? What is space-time made of? Is it a thing, a substance, a medium? Or is it just a mathematical convenience, a set of equations that happen to predict the right answers without corresponding to anything physically real? Newton refused to answer this question about forces. Einstein refused to answer it about geometry. And a century after general relativity, we still cannot answer it. The most successful theory of gravity in human history tells us that mass curves space-time, and that curvature is gravity. But when you ask what space-time is, the theory goes silent. This is not a philosophical quibble. It is a concrete, testable gap in our understanding. And the sun disappearing for 1 second, impossible as it is, turns out to be the perfect thought experiment for exposing that gap, because it forces you to trace the entire chain of reasoning. The sun vanishes. Information about the vanishing propagates at c. The propagation is a change in space-time geometry. But what carries the change? In electromagnetism, a change in the electric field propagates as a photon. What is the gravitational equivalent? General relativity says the change is a ripple in space-time itself. But space-time in general relativity is not made of anything. It is the background on which everything else happens. The stage, not the actor. So how does the stage ripple? This is the question that quantum gravity is trying to answer. And it is the question that remains open as of right now, today. String theory proposes one answer. Loop quantum gravity proposes another. They are incompatible, and neither has been experimentally tested. The thought experiment about the sun disappearing for 1 second leads, if you follow it far enough, straight into the deepest unsolved problem in physics. But before we go there, let us do something that might seem like a detour, but is actually the key to understanding just how strange the speed of gravity makes our solar system. Let us trace what happens to every planet, because the disappearance does not happen everywhere at once. It ripples outward, and each planet experiences the 1 second gap at a different time, in a different way, with a different magnitude. The solar system is not a collection of objects responding simultaneously to the same event. It is a chain of dominoes falling outward at the speed of light, and the dominoes are not even aware of each other. Mercury is closest to the Sun, orbiting at an average distance of about 58 million kilometers. The gravitational news arrives after 3 minutes and 12 seconds. Mercury moves faster than any other planet, 47.87 kilometers per second, screaming around its tight orbit. During the 1 second gap, it deviates about 20 millimeters, roughly the width of your thumb. Mercury also has the most eccentric orbit of the major planets, so the exact deviation depends on where it is in its orbit when the gap arrives. At perihelion, When it is closest and moving fastest, the deviation is larger, at aphelion, smaller. But in all cases, it is a distance you could cover by pressing your thumb against a ruler. Venus is next, 91 million kilometers farther out. The gap arrives after 6 minutes. Venus orbits at 35 kilometers per second, slower than Mercury, but still fast enough to cross the length of Manhattan in about half a second. Its deviation is 5.7 millimeters, less than the width of a pencil. Earth, as we have calculated, gets its 3 millimeters after 8 minutes and 19 seconds. Mars, at 228 million kilometers, waits 12 minutes and 42 seconds and deviates 1.3 millimeters, less than the thickness of a credit card. By the time you reach the outer solar system, the numbers become almost comically small. Jupiter, the largest planet in the solar system, a world so massive it could swallow 1,300 Earths, orbits at 778 million kilometers from the Sun. The gap reaches it after 43 minutes and 18 seconds. Jupiter orbits at 13 kilometers per second. Its deviation is 0.11 millimeters, about the width of a human hair. Saturn, at 1.4 billion kilometers, gets the news after 79 minutes. Its deviation is 0.03 millimeters. That is 30 micrometers, roughly the diameter of a fine grain of pollen. Neptune, the outermost major planet, orbits at 4.5 billion kilometers. The 1 second gravitational gap does not arrive until 4 hours and 10 minutes after the Sun vanishes, and by then, the Sun has already been back for 4 hours, 9 minutes, and 59 seconds. Neptune's deviation is 3 micrometers, 0.003 of a millimeter. You would need a good microscope to see a distance that small. But the solar system does not end at Neptune. The gravitational shell keeps expanding. Voyager 1, the farthest human-made object from Earth, is currently about 24 billion kilometers from the Sun. The gravitational gap would reach it after roughly 22 hours. By then, the Sun has been back for 21 hours, 59 minutes, and 59 seconds. Voyager is barely crawling at 17 kilometers per second, less than half of Earth's orbital speed, and the Sun's gravity at that distance is vanishingly weak. Voyager's deviation during the 1 second gap would be measured in nanometers, billionths of a millimeter. The thermal expansion of its metal hull from a fraction of a degree of sunlight warming produces larger distance changes than this. And beyond Voyager, the shell keeps going. The Oort cloud, that vast spherical shell of icy bodies that marks the true gravitational boundary of the solar system, extends out to perhaps 100,000 astronomical units, roughly 1.5 light years from the Sun. The 1 second gap would not reach the far edge of the Oort cloud for about a year and a half. A comet at the outer Oort cloud orbits the Sun at a speed so slow it is barely drifting, perhaps a few meters per second. The Sun's gravitational acceleration at that distance is roughly 10 to the minus 13 meters per second squared. The deviation from a 1 second gap would be on the order of 10 to the minus 14 meters. That is smaller than the nucleus of an atom. And there is something profound hiding in these numbers. Every single one of these objects, from Mercury to the outermost comets of the Oort cloud, continues orbiting normally for minutes or hours or months after the Sun has already vanished. They are all orbiting a ghost, just like Earth. Mercury orbits the ghost for 3 minutes. Neptune orbits the ghost for 4 hours. During that time, the Sun is not there, but the space-time curvature it created is. The curvature is not a memory or an echo. It is physically real. It carries energy. It determines trajectories. The geometry left behind by a mass that no longer exists is, for all practical purposes, indistinguishable from the geometry produced by a mass that still does. Until the information arrives, the distinction between present mass and absent mass does not exist. It is not that the planets are fooled. There is genuinely nothing to detect. The space-time around them is identical in both cases. This is one of the deepest consequences of general relativity, and it is the reason Einstein's theory is so fundamentally different from Newton's. In Newton's universe, the Sun's gravity is a force that exists because the Sun exists. Remove the Sun, remove the force, instantaneously, everywhere. In Einstein's universe, the Sun's gravity is the shape of space-time, and that shape has its own physical reality. It persists until new information overwrites it. The shape is not caused by the Sun in real time. It was caused by the Sun in the past, and it propagates outward at a finite speed, constantly being updated. What you feel right now is not the Sun's current gravitational influence. It is the gravitational influence the Sun had 8 minutes and 19 seconds ago. You are always orbiting the past. There is a beautiful irony in the fact that the first experimental evidence for the speed of gravity came not from measuring how fast it travels, but from measuring how much energy it carries away. In 1974, 2 physicists at the Arecibo Observatory in Puerto Rico discovered something remarkable. Russell Hulse was a graduate student. Joseph Taylor was his advisor. They were surveying the sky for pulsars, rapidly spinning neutron stars that emit beams of radio waves like cosmic lighthouses. On July 2nd, Hulse detected a pulsar with an unusual signal. Its pulse period was not constant. It varied in a regular pattern, speeding up and slowing down over a cycle of about 7.75 hours. This meant the pulsar was in orbit around something. The Doppler effect was compressing and stretching the pulse timing as the pulsar moved toward and away from Earth along its orbit. Hulse was a graduate student running through a survey, cataloging pulsars one after another. He almost missed it. The initial detection was a 7.25 sigma signal, just barely above the 7 sigma threshold he was using. A slightly different threshold, and he would have moved on to the next patch of sky without a second look. The something turned out to be another neutron star. 2 dead stars, each roughly 1.4 times the mass of the Sun, packed into spheres about 12 kilometers across, orbiting each other at blistering speed. At their closest approach, they were separated by only about 1.1 solar radii, closer together than the Sun's own diameter. They were moving at roughly 300 kilometers per second, 1/10 of 1% of the speed of light. This system, designated PSRB 1913+16, was a gravitational laboratory. Einstein's field equations make very specific predictions about what happens to such a system. The 2 neutron stars, spiraling around each other, should produce gravitational waves. Those waves should carry energy away from the orbit, and as the orbit loses energy, the 2 stars should spiral closer together, orbiting faster and faster. Taylor and his colleagues monitored the system for years, then decades, and the orbital period was indeed decreasing by about 76.5 microseconds per year. That means each orbit is getting shorter by 76.5 millionths of a second per year. The orbit was shrinking by about 3.1 millimeters per revolution. Not per year, per revolution. Every 7.75 hours, the two neutron stars were 3 millimeters closer together. 3 millimeters. The same number as Earth's deviation in our thought experiment. A coincidence, but a pleasantly symmetric one. The critical question was whether the rate of orbital decay matched what general relativity predicted. If gravity waves carry energy, and if they carry it at the rate Einstein's equations specify, then the orbit should decay at a very specific rate. Taylor's team compared the observed decay to the prediction. The ratio of observed to predicted was 0.997, plus or minus 0.002. That is agreement to within 0.3%. Not approximately right, not in the right ballpark, essentially perfect. This was the first experimental confirmation that gravitational waves carry energy, and it was the first evidence that the speed of gravity is finite. Because the rate at which gravitational waves carry energy away depends on the speed at which they propagate. If gravity were instantaneous, the energy loss rate would be different. The Hulse-Taylor system's orbital decay matches the prediction for gravitational waves traveling at c, not at 7 million times c, as Laplace calculated, not at infinity, as Newton's equations implied. At c, Hulse and Taylor received the Nobel Prize in Physics in 1993, 21 years before LIGO's direct detection. The indirect evidence had been compelling for decades, but indirect evidence and direct detection are not the same thing. Nobody had heard a gravitational wave. Nobody had felt space-time stretch and compress. The Hulse-Taylor result showed that the energy budget was consistent with waves traveling at c. It was as if you could hear a bell ringing in the next room and measure the vibrations in the floor, and everything was consistent with sound waves traveling at 343 meters per second. But you had never actually put a microphone in the room to record the sound itself. The inference was convincing. The proof was not yet complete. LIGO showed the waves themselves. GW 170817 measured their speed. 3 experiments, 3 levels of proof: indirect, direct, and measurement. Each one confirming the same thing Newton could not explain. Laplace got wrong, and Einstein predicted but doubted. There was one more attempt to measure the speed of gravity before LIGO, and it is worth mentioning because of what it reveals about how careful you have to be when claiming to measure something this fundamental. On September 8, 2002, the planet Jupiter passed very close to the line of sight between Earth and a distant quasar called J0842 plus 1835. Sergei Kopeikin, a physicist at the University of Missouri, and Ed Fomalont, a radio astronomer at the National Radio Astronomy Observatory, used very long baseline interferometry to measure how Jupiter's gravitational field bent the quasar's radio waves during the close approach. Their idea was elegant. As Jupiter moved across the sky, its gravitational field would shift and the deflection of the quasar's light would change. The rate at which the deflection changed depended, Köpeken argued, on the speed of gravity. If gravity propagated instantaneously, the deflection would track Jupiter's current position perfectly. If gravity propagated at sea, there would be a tiny correction. They announced their result in January 2003. The speed of gravity, they said, was 1.06 plus or minus 0.21 times the speed of light, consistent with C. Front-page news around the world. But the physics community pushed back hard. Clifford Will, one of the world's leading experts on experimental tests of general relativity, published a detailed rebuttal. His argument was subtle but devastating. The effect Köpeken and Fomalhaut measured was real, but it was not measuring the speed of gravity. It was measuring the speed of light. Here is why. In the reference frame where Jupiter is stationary, Jupiter's gravitational field is static. Birkhoff's theorem again. A static field does not propagate. It just sits there. The only thing traveling at a finite speed in this scenario is the quasar's light, which is passing through Jupiter's static field. The deflection depends on the speed of light, not the speed of gravity, because the field itself is not moving. Transform to a frame where Jupiter is in motion and you get velocity-dependent corrections. But those corrections are also determined by the speed of light, not gravity. Will was blunt about it. The real way to measure the speed of gravity, he wrote, is to detect and study gravitational waves. Full stop. Köpeken disagreed. The debate went back and forth in the journals for years, but the consensus eventually sided with Will. The quasar deflection experiment was a beautiful measurement of how light propagates through a gravitational field. It was not a measurement of how fast that field itself changes. The distinction sounds academic, but it is exactly the distinction that matters for our thought experiment. When the sun vanishes, what we want to know is how fast the change in the gravitational field propagates outward, not how fast light moves through the field. Those are different questions, and they require different experiments. LIGO and GW170817 answered the right question. Let us return to scale for a moment, because the numbers we have been throwing around are difficult to feel, and I want to make sure they land. The sun puts out 3.82, 8 times 10 to the 26 watts. That number means nothing by itself. So let us translate it. Every single second, the sun releases as much energy as 1.83 billion Tsar bomba. Nuclear weapons detonated simultaneously. The Tsar bomba was the largest nuclear device ever tested. 50 megatons detonated by the Soviet Union in 1961. The fireball was 8 kilometers across. The mushroom cloud rose 67 kilometers into the atmosphere. The shockwave circled the Earth 3 times, and the sun matches 1.83 billion of those every second for 4.5 billion years. Without pausing, Earth catches 2.2 billionths of that output. One tiny sliver of light hitting a tiny blue marble in the vastness of the solar system. And that tiny sliver is everything. It is the entire energy source for every weather system, every ocean current, every photosynthetic organism, every calorie in every piece of food you have ever eaten. The sun's gravity holds us in orbit, but the sun's light keeps us alive, and we are catching 2.2 billionths of it. Now take that sliver away for 1 second. The missing energy, after accounting for the partial dimming profile and Earth's reflective albedo is about 1.22 times 10 to the 17 joules. For comparison, the total energy consumption of human civilization in an entire year is about 5.8 times 10 to the 20 joules. So the energy Earth misses during 1 second of solar absence is about 1/50,000th of humanity's annual energy use. It is the energy equivalent of roughly 23 billion kilowatt hours, about enough to power the United States for 2 hours. That is real energy. It is not zero, but spread across the entire surface and thermal mass of the Earth, it is swallowed without a trace. The ocean absorbs it, the atmosphere absorbs it, the ground absorbs it, and none of them notice. Here is another way to feel the 3 millimeter orbital deviation. Earth's orbit is not a perfect circle. It is an ellipse with an eccentricity of 0.0167. That means the distance from the Sun varies by about 5 million kilometers over the course of a year. Earth is closest in January, farthest in July. That 5 million kilometer variation is the natural wobble of our orbit, caused by the same gravitational dynamics that Laplace spent his career mapping. The 1 second disappearance adds an eccentricity change of about 2 times 10 to the -7, 2/10 millionths. The existing eccentricity is 0.0167. The new eccentricity is 0.01670002. The change is 84,000 times smaller than the eccentricity that already exists. And the eccentricity that already exists is so small that most people do not even know Earth's orbit is not circular. But you know what is even more humbling? Jupiter's gravitational pull on Earth causes perturbations to our orbit that are roughly 10 million times larger than the effect of the Sun's 1 second absence. 10 million times. Every single orbit, Jupiter tugs on us more than our thought experiment disturbs us. The Sun vanishing for a second does less to Earth's orbit than Jupiter does just by existing on the other side of the solar system. Rainer Weiss died on August the 25th, 2025. He was 93 years old. He had lived long enough to see the machine he designed in a 22-page technical report in 1972 become the most sensitive measuring device in human history. He had lived long enough to hear the chirp of merging black holes, to measure the speed of gravity to 15 decimal places, and to accept a Nobel Prize for a discovery he had spent his entire career working toward. But what I find most remarkable about Weiss is not the Nobel Prize or the discovery. It is the 1972 document. Because in that document, written at MIT and published in an internal quarterly report that almost nobody read, Weiss did something extraordinary. He identified every significant source of noise that would affect a laser interferometer, gravitational wave detector, seismic noise, thermal noise, photon shot noise, residual gas in the vacuum chambers, radiation pressure from the laser on the mirrors. He did not just list them. He calculated their magnitudes. He derived the equations. He worked out the arm length required to achieve the necessary sensitivity. 4 kilometers. He was right. It took 43 years to build what he described, and when it was built, it worked the way he said it would. This is the kind of story that does not usually get told in science documentaries because it is not dramatic in the usual way. There is no eureka moment. There is no flash of genius at a blackboard. There is a man sitting in an office at MIT doing careful engineering calculations for a device that would not exist for half a century, getting the details right on the first try. Kip Thorne provided the theory. Barry Barish provided the organizational genius. But Weiss provided the blueprint, and the blueprint was correct. He lived to see the whole arc. From a 22-page report that nobody read, to a billion-dollar instrument that detected ripples in spacetime from events that occurred before the Earth existed, from an idea that most physicists considered a fantasy, to a measurement so precise that it confirmed a prediction Einstein himself had doubted. And this brings us back to where we started. What would happen if the sun disappeared for 1 second? The honest answer is that the question itself is more interesting than any answer could be. The sun cannot disappear. The laws of physics forbid it. Conservation of energy is not a suggestion. It is woven into the mathematical structure of spacetime. Birkhoff's theorem means a spherically symmetric mass cannot change its external gravitational field without sending something outward at or below the speed of light. The equivalence principle means you cannot locally detect the difference between gravity and acceleration, which means you cannot locally detect the absence of gravity during freefall. Every piece of general relativity conspires to make the scenario impossible and, even if it were possible, undetectable. But the impossibility is the point. The thought experiment is a machine for generating insight. You start with a simple question. What happens if the sun blinks out for a second? And the question leads you through 300 years of physics. You learn that Newton knew his own theory was incomplete, but could not fix it. You learn that Laplace asked exactly the right question with exactly the wrong theory, and got an answer that was off by a factor of 7 million. You learn that Einstein found the right answer, but then spent 20 years trying to take it back. You learn that a graduate student named Russell Hulse, surveying the sky with a radio telescope in Puerto Rico in the summer of 1974, stumbled across a binary pulsar whose orbital decay would become the first evidence that gravitational waves carry energy at the speed of light. You learn that a man named Rainer Weiss, in a document nobody read, designed a machine that would not be built for 4 decades, and then worked exactly as described. You learn that the universe, when finally given the chance to answer the question, answered it with a pair of neutron stars that collided 130 million years ago and delivered their message to within 1.74 seconds of the photons that traveled beside them. And at the end of all of it, after the 3 millimeters and the 24 millionths of a degree, and the 3-second flicker, and the 4 hours it takes Neptune to find out, and the 15 decimal places of precision, you are left with the same question Newton was left with in 1693. How does gravity cross empty space? Einstein replaced the question with a different one. What is space-time, and why does it curve? And that question remains unanswered. The deepest thing the thought experiment teaches you is not what happens when the sun disappears. It is that we still do not fully understand what gravity is. Newton described it. Einstein redescribed it. We measured it. We confirmed its speed. We detected its waves. We watched it shape the orbits of planets and the mergers of neutron stars. But what it is, what space-time is made of, why mass tells space to curve and curved space tells mass to move, that is still open. 328 years after Newton called it absurd, And 110 years after Einstein wrote down the equations, the mechanism of gravity remains the deepest open question in physics. Newton wrote in his letter to Bentley that gravity must be caused by an agent acting constantly according to certain laws. But whether that agent is material or immaterial, he wrote, I have left to the consideration of my readers. More than 3 centuries later, we are still his readers, and we are still considering. General relativity describes the agent beautifully. It is space-time curvature. The description makes predictions that are correct to 15 decimal places. But a description is not an explanation. Space-time curvature tells us what gravity does with extraordinary precision. It does not tell us what gravity is. Newton's hypotheses non fingo, his refusal to speculate about causes, has been inherited by every generation of physicists since. We describe, we predict, we measure, we confirm. But the explanation, the true mechanism by which one mass tells another mass it exists across the emptiness of space, remains beyond us. The sun disappearing for 1 second would do almost nothing to the Earth. But the question of how the Earth would find out about it has driven 3 centuries of science, produced some of the most beautiful mathematics ever written, inspired some of the most sensitive instruments ever built, and brought us face to face with the limits of our understanding of the universe. 3 millimeters. That is all the Earth would notice. But the 3 millimeters contain the whole history of gravity. And the history is not over yet.